In this video, we're going to cover the structure and properties of alkenes, looking at their structure and the different tests for alkenes, the electrophilic addition mechanism, looking at how to write equations first, then the general mechanism, some specific examples of that mechanism, and then looking at how carbocations can influence the major and minor products formed during this reaction. And addition polymerisation, looking at how to represent and name polymers, and then the different properties of polymers, looking at the forces between the chains and the roles of plasticizers. We're going to start off by looking at the structure and properties of alkenes. An alkene is a chemical with at least one carbon-carbon double bond in it. So we can say that these molecules are unsaturated. This is because they can make more bonds in addition reactions, and we'll look at those reactions later on. Since they can make more bonds in reactions, we can say they are quite reactive chemicals. And the reason they are reactive and they can make additional bonds is that the carbon-carbon double bond is an area of high electron density, as we can see by the diagram on the right of the screen. The double bond is obviously two sets of bonds there, two sets of shared pairs of electrons. Therefore, there's quite a lot of electron density around those atoms, and later in this video we'll look at the mechanism through which that causes the alkene to react. We're now going to look at some examples of common alkenes, how to name them and how to draw them. So to start off with, we'll look at propene. And we've drawn the displayed formula for it here. You can see the stem of the name starts with prop, so there'll be 3 carbons in the chain. We've got our ene, which means we've got a double bond. Remember, unless the name tells you otherwise, for example being a diene, there is just one double bond per alkene. And this is how we could write the structural formula for protein, showing what is attached to each carbon, atom by atom. As I've just mentioned, sometimes you can have alkenes which have got more than one carbon-carbon double bond in. So for example, if we look at penta 1,3-diene, that would be a molecule which has got 5 carbons in its chain, but with double bonds on carbons 1 and carbons 3. So we can see we've got a diene because there are 2 carbon-carbon double bonds present. And this is what the structural formula for penta 1,3-diene would look like. Again, just writing the formula carbon by carbon. You can also have cycloalkenes, just like you can have cycloalkanes. So in this case, cyclopentene. This would be the skeletal formula for cyclopentene. So pent means there are 5, therefore we've got a 5-membered ring, and a ring because it is cyclo, it is a cyclic molecule. And in this case, we would just use the molecular formula to represent a ring like this, being C5H8. Note that it doesn't form what you might consider the typical general formula of an alkene to be CnH2n, because we have got less hydrogens available on these atoms here, because they've got additional bonds to carbon with the double bond, and it being in a ring structure. So be careful if you're working out the molecular formula of a cycloalkene. It's probably better to draw it out displayed and count the carbons manually in that case. You need to know the chemical test for an alkene. It is something you will have covered at GCSE, but we'll recap it here. The test is to add bromine water, and we will say that the bromine water has been decolorized. This means it's gone from being orange to being colourless. Make sure you say it has gone colourless and not gone clear. They are 2 different things. Clear means you can see through the chemical, as in it's the opposite of being cloudy, but you can still have clear coloured solutions. You could have a clear blue solution, for example. In this case, we need to be very clear. The colour started off being orange, and then it no longer has a colour, so it is colourless. We're now going to look through the electrophilic addition process, the process through which alkenes react. Before we can start off though, we need to look at what electrophiles are. An electrophile is an electron pair acceptor. In the previous topic, you learnt what a nucleophile is, an electron pair donor. An electrophile is essentially the opposite of that. It's an electron pair acceptor. These are some of the common electrophiles you'll come across in A-Level Chemistry. You'll notice some of them have got positive charges, which makes sense if they want to accept a pair of electrons, which will be negative, but not all of them do. These two electrophiles, where we've written the X, could be replaced with any halogen. So for example, HCl, HF, HI, or Cl2, I2, F2 would work in exactly the same way as HBr and Br2. We're now going to look at the general equation for an electrophilic addition process. We'll look at specific examples later on. In an electrophilic addition reaction, an alkene will react with a molecule in the form of XY. Now, X and Y could be individual atoms, so you could say have H and Cl, or they could be two different halves of the molecule. For example, the X could represent the H, and the Y could represent an OH in water, for example. So they could either be separate atoms or separate parts of the molecule. That will make more sense when we look at the specific examples of this in a moment. The product of this reaction is where we add the X onto one carbon of the alkene double bond and the Y onto the other carbon of the alkene double bond. To help us visualise this, we'll now look at this as a displayed formula. So we've got our starting material, our alkene, and our electrophile in the format of XY. And as we can see in the product, we've added the X onto one carbon and the Y onto the other carbon. So we've gone from being an alkene to a new molecule which is now saturated. We can't add any more bonds onto this molecule. So for example, we might have an alkene reacting with Br2. In this case, the Br would be both the X and the Y because there are two of them, Br, Br, in which case we would add a bromine onto each of the two carbons. We could do the same reaction with HBr instead of Br2. In this case, we'd add the H onto one of the carbons and the Br onto the second carbon. And in the final example, we've added water, as we mentioned earlier. In this case, we would add the H of the H onto one carbon and the OH onto the second carbon. Again, showing how the X and Y doesn't have to represent two specific atoms, it could represent two halves of a molecule. In the previous topic, you looked at nucleophilic substitution mechanisms. We're now going to have a look at the mechanism for electrophilic addition. In an electrophilic addition reaction, the double bond in an alkene opens up and attacks an electrophile. An alkene is not a nucleophile itself. The electrons in the attack come from the bond, not from a lone pair. The carbon-carbon double bond in the alkene repels the electrons in our XY molecule. This polarises the XY bond. Sometimes the XY bond could already be polar, as in the case of, say, HBr. So our first step is to draw our partial charges on. If we have got two atoms which are identical, for example, two bromines, just label the first one as being slightly positive and the second as being slightly negative. This is because the electrons in this molecule are being repelled by the double bond. So there's lots of negative electrons in the double bond, and that pushes the electrons in this shared pair as far away from the double bond as it can. So the electrons will get pushed to this side of the molecule, so the atom on the end here will be slightly negative, and the atom on the front will be slightly positive. If this was, for example, HBr, then we'd write the H in the first position because we know that hydrogen is more electropositive than bromine, which is electronegative. but we'll look at specific examples later on. Two electrons from the carbon-carbon double bond attack the X atom, creating a new bond between the carbon and the X. So we'd represent this with our curly arrow. This causes the XY bond to break, and the electrons from the bond are taken by the Y atom to form a negative ion, as it will now have a lone pair of electrons. So this will be the product after we've drawn both of these curly arrows. We've got the new bond between the C and the X. We've lost the Y and it has a negative charge. This carbon here is left with a positive charge, since when the double bond broke, the first carbon took the electrons to form a bond with the X atom. Therefore, this carbon is lacking a bond, so it has a positive charge. We call this a carbocation. The Y ion will then act as a nucleophile. It will have a lone pair of electrons. The Y will then donate the pair of electrons to the carbon, so it will attack it. We will draw a new curly arrow between the Y minus and the carbocation, forming a new bond between the C and the Y, completing the mechanism. We're now going to look at two specific examples of this mechanism, starting with Br2. The first step is to write out the equation, so we know we're using the correct starting material and forming the correct product. And we'll then draw out the displayed formula of both the reactants involved. We then need to add in the partial charges on our electrophile. Given that both of these atoms are the same, we can say that the first bromine will be slightly positive because it's closest to the double bond, so its electrons will be repelled by being close to the double bond. The second bromine will be partially negative. Now we've labelled those partial charges, I've just removed them so we've got space to draw the arrows. You can also leave these on your diagrams. The first step in the mechanism is for the carbon double bond to attack the bromine, which was slightly positive, and then to break the bromine-bromine bond, moving the electrons from the bond onto the second bromine, the one which was slightly negative. Our product will have the carbon with a new bond to the bromine from the process we did in the first step. The second carbon, its double bond was broken without gaining a new bond, so it is positive, it is a carbocation. And the bromine, which gained the electrons during the second step, has now got a negative charge by itself over here. To complete the mechanism, we then add the lone pair onto that bromine ion, and it attacks the carbocation, which will form a new bond between the carbon and the bromine, giving us our final product. In this example, we're going to look at how we can add sulfuric acid to an alkene. The equation for this process is slightly complicated, and you will need to learn this for your exam. In this case, the sulfuric acid is actually acting as a catalyst to add a molecule of water. We only need to learn the mechanism for the role the sulfuric acid plays in attaching itself to the alkene. This will become clear as we look at the mechanism. Earlier on in the video, we looked at the equation for adding an alkene to water to make an alcohol, but this process actually requires the sulfuric acid catalyst, and it's the sulfuric acid catalyst which does the electrophilic addition mechanism we've just looked at. So there are actually two different steps to this process. We're going to draw the mechanism for this first step here, showing adding sulfuric acid, which has got the formula H2SO4, to our alkene, and we'll form this product. The product might look slightly complicated, it isn't, it will make sense when you look at the displayed structure of it. In a second step, which we don't need to learn the mechanism for, there isn't a mechanism you learn for this specific step in this topic, by adding water to the product we made in step 1, that then turns this product into being an alcohol, and the sulfuric acid is regenerated at the end, As the sulfuric acid is regenerated at the end, we can say it is a catalyst. The first step then is to draw the displayed formula of our alkene, and then the displayed formula of sulfuric acid. You might not have come across the displayed formula of sulfuric acid before, but we can't just write it as SO4. We have to draw it out like this. So sulfuric acid is a sulfur where 2 of the oxygens are double bonded and it contains 2 OH groups. We've drawn out one of the OH groups here explicitly as a H bonded to an O, because this is where the mechanism is going to take place. You can leave the other OH group shortened as I've done here. Now we'll know that the hydrogen is going to be slightly positive and the oxygen is going to be slightly negative. Because of the work you've done in physical chemistry, you know that oxygen is more electronegative than hydrogen. So therefore, this doesn't really take into account the repulsion from the bond. We could label these polarities just like we did in the previous topic by ourselves. The first step is that the double bond is going to attack the hydrogen, and we'll represent that using a curly arrow. This will then cause the HO bond to break, meaning that this oxygen here will then have a lone pair. Our products are drawn in exactly the same way as before. We've now made a new bond between this carbon and the hydrogen, as shown here. We've got our carbocation, our carbon with a positive charge, and our sulfuric acid now just has the oxygen with a negative charge. The rest of the molecule is unchanged. Remember to make sure you draw the rest of it out. The final step still follows the same format. The lone pair on the oxygen will attack the carbon, forming a new bond between the oxygen and the carbon. And this gives us the displayed formula here of the structural formula of our product, which we said might look a little bit complicated at first, but now you've seen sulfuric acid drawn out, we can see that we've got a CH3 group, a CH2, and then attached to the CH2 is an O, an S, with 2 oxygens, and an OH group. So the structural formula, once you've done the mechanism, is quite straightforward. So far we've been looking at simple alkenes which only have 2 carbons in them. However, if you've got more carbons present, for example from propene onwards, you could end up with having a choice of products. We're going to look at how to decide what product you would make. So for example, we've got propene here, and let's say we were adding HBr to the molecule. You could end up with this product on the left. You could add the hydrogen to the carbon on the left of the double bond, and the bromine to the carbon on the right of the double bond. Or alternatively, you could add the hydrogen to the carbon on the right of the double bond, and the bromine to the carbon on the left of the double bond. And you'll see here these are 2 very different products. We could either form 2 bromopropane or 1 bromopropane. Only one of these is correct. There is a reason why one of these is formed as opposed to the other. We're now going to look in detail about how you would decide what the correct product is, called the major product, and to be able to explain why it is formed over the other one, which is called the minor product. In order to understand which product is formed though, we need to go back to those carbocations we formed during the mechanism and learn a little bit more about them first. So to recap the mechanism we've just covered, the double bond attacks one of the atoms in the electrophile, causing the electrophile to split apart, giving us 2 products, the carbocation and our negative ion. This entire molecule is the carbocation, not just the carbon here. Whatever is remaining can be referred to as the carbocation. There are three different types of carbocations, all depending on how many different groups, which aren't hydrogen, are attached to the carbon. In this case, we're going to use R to represent the rest of the carbon chain, because it doesn't matter how many carbons are in the rest of the chain. So this could represent a CH3 group, a C2H5, C3H7, it doesn't matter. This just means it's not a carbon attached to the carbon. So in this case, this carbocation has got two hydrogens attached to the carbon and one carbon chain heading off in this direction. You could have a carbocation with two carbon chains attached to the carbon with a positive charge and one hydrogen on it. Or you could have a carbon with a positive charge with three carbon chains coming off it. If a carbocation only has one carbon chain attached to the carbon with a positive charge and the rest are hydrogens, we say that is a primary carbocation. If the carbon with a positive charge has got two carbon chains coming off it and one hydrogen, we say that is a secondary carbocation. And if the carbon with a positive charge has got three carbon chains coming off it, then we say that is a tertiary carbocation. Alkyl groups, or the carbon chain groups, are what we call electron donating. They can push their electron density towards the carbon. This will help stabilise it. So a primary carbocation has got one stabilising or one electron donating group attached. The reason it's stabilised is if you imagine the electrons being pushed towards the carbon, those negative electrons are going to balance out that positive charge a little bit. So a secondary carbocation would have two stabilising groups attached, two groups donating electron density to help balance out that positive charge. And a tertiary carbocation would have three electron donating groups or three stabilising groups to further reduce the positive charge. So this means that the primary carbocation is the least stable of the three, the secondary is in the middle, and the tertiary carbocation is the most stable of the three. And this makes sense, as the tertiary carbocation has got the most electron stabilising groups attached. It's got three groups donating electron density, compared to the primary, which has only got one. So the tertiary will have in effect a smaller positive charge than the primary, and that makes the carbocation more stable. We'll look at why this is important when we revisit the mechanism in a moment, but you've got to be happy to explain which of these is the most stable. So in general, is a primary, secondary or tertiary more stable? And why is that the case? And that's always linked to the number of alkyl groups attached. We're now going to use what we've just learnt about carbocations to work out the structure of a product from a given reaction. For example, we're now going to name the major product formed in the reaction of propene with hydrogen bromide. We'll explain why the major product is formed. We'll start off by drawing out the structure of propene, and then we'll draw the hydrogen bromide underneath it. The first step of the mechanism is for the carbon-carbon double bond to attack the hydrogen, causing the hydrogen-bromine bond to break. We'll then draw the structures of the two possible intermediate structures we could form. So we could have the positive charge on the middle carbon, or we could have the positive charge on the beginning carbon, depending which way this bond broke. We'd then need to decide which was the most stable carbocation intermediate. Using what we've just learned, this carbocation intermediate here has got two carbon groups attached to it, while this one here has only got one. Therefore, this is a secondary carbocation, and this is a primary carbocation. We know that secondary carbocations are more stable than primary carbocations, so the mechanism will carry on, but using this intermediate here. We'll now carry on with the second stage of the mechanism. So we've got our positive charge on the second carbon and our bromine. The bromine will have a lone pair which will attack the positive carbon, giving us our final product. We'll now need to explain why this product was formed in a couple of sentences. And we can say that 2-bromopropane is the major product because it is formed via the most stable carbocation intermediate, a secondary carbocation compared to a primary carbocation. In an explanation for why the major product was formed, you've always got to say the name of it, that it was formed as the major product through the most stable carbocation intermediate, and compare the two carbocations that you looked at. So for example, in this case we're comparing secondary against primary, but in your answer you might end up comparing tertiary against secondary, tertiary against primary. You've always got to state which kind of carbocations were involved. We're now going to look at the next part of this topic, which is looking at polymers. Alkenes are monomers, which means they can react together to form a polymer. You'll have several different alkene molecules joining together. So for example, let's say we've got 3 molecules of ethene, and they could form a polymer chain like this. This builds on the work you've done at GCSE, but you'll know from GCSE the double bond in the carbon can open up, linking with other alkenes and forming a long chain. We can simplify how we write this process to take into account N starting monomers. So we'd write our alkene or our monomer out, and we'd put an N in front of it to represent however many monomers we wanted to start with. We then draw our polymer in the curly bracket formation. So we remove the double bond and replace it with a single bond. We extend the trailing bonds from each carbon, so adding these bonds here, making sure our brackets go through the trailing bonds, and having an N at the end, which will obviously be the number of repeating units based on the number of monomers we started with. Sometimes you'll be given a polymer chain, and you'll have to identify either the repeating unit or the monomer which formed that polymer. So for example, we've got a long chain here, and we'll need to identify what the repeating unit is. This one is relatively straightforward, as we can see that 2 carbons with hydrogen and then a chlorine, and each attached to another hydrogen, is the repeating unit in this case. So we could draw out our repeating unit like this. And we can then change it back into the alkene monomer by realising that the bond in the middle of the repeating unit will be our double bond. We'll lose the trailing bonds on each side, as it's going to be the monomer and no longer part of the main polymer chain, and our 4 groups attached to the carbons will stay exactly as they were. We're now going to look at the different kinds of intermolecular forces which occur between different polymer chains. Alkene monomers are unsaturated, they have a carbon-carbon double bond, while the polymers are saturated, they don't have a double bond. Polyalkenes are non-polar, they've just got carbons and hydrogens in, there are no polar bonds, no bonds with a difference in electronegativity. This means the chains aren't susceptible to nucleophilic attack, so you won't get a nucleophilic substitution reaction happening within the polymer chain, for example, and this makes the chains very unreactive or inert. The monomers within a polymer have strong covalent bonds. However, the intermolecular forces between the polymer chains are much weaker. This polyalkenes chains can pack very closely together as there aren't any branches to push the chains apart. This means there'll be lots of van der Waals forces between the chains, and this will make it very strong and rigid. This polymer contains a large branch, so the chains won't be able to pack closely together. We can see here, this is a benzene group. You'll learn about this in your year 13 studies. It's not important for the moment, apart from the fact it's a branching group, it's coming off the main chain, and it's forcing those chains to be further apart. Therefore, there'll be less van der Waals forces between the chains, and this makes the polymer more flexible. This polymer contains polar covalent bonds which will result in permanent dipole forces between the chains. The chlorines are slightly negative, making the carbon slightly positive. And this will occur on all the chlorines and carbons within the polymer. So we can see how we'd have a permanent dipole interaction between the carbon on one chain and the chlorine on another. This makes the polymer hard but brittle. This particular example is PVC. It's typically the white plastic used on window frames. Adding plasticizers to a polymer will modify its properties. These chemicals make the polymers bendier. The plasticizer molecules get between the polymer chains and pushes them apart. This reduces the strength of the intermolecular forces between the chains. Therefore, the chains can slide around more, making them more flexible. So typically, plasticizers will be added to things like wire cables, so what goes on the end of a plug, so that wire can bend, it can be flexible, but it's still got the strong properties of the polymer.